This video looks at finding areas and curves where we have more complex curves or possibly two curves. Example 3 in two curves. As you can see, I've already drawn the diagram, which you'll do with the assistance of your calculator. So here are 3 cos theta, which is the circle, and then we've got the cardioid and this equation. Now they're asking me to find the exact area of the region which lies between both curves. So that means section above, below the initial line. When I'm thinking about polar areas, I have to think about increasing my angle and the sector that forms. So I'm going to need the area starting at the initial line and going with this angle. That's going to be the area created by cardioid. I'm then also going to need this area above this line, and that is going to be from this line, this curve, and this curve is the circle. So I'm going to need to find both these areas, and I'm going to together. And then I also want the area underneath the initial line, so I will. So we've got 2 integrations to do, and we've got to think carefully about the limits that we're going to use for those integrations. We need to know the angle where this dotted line is, and that's where part B comes in, because it asks us to find the points of intersection between the 2 curves, which will be this point here and then also this. So what we're going to do is we're going to find that coordinate there, and then we're going to work out this area and then this area, and then we're going to double them. And at the end, we'll talk about whether I can just simplify my working slightly to make these questions as simple as possible in terms of their working. So let's do part B on finding the points of intersection. So we've got 2 curves. They are 1 plus theta and 3 cos. So I equate those and we get cos theta r. So that gives me theta equals initial value of pi over 3. And looking at the curve, I'm going to want this one down here, aren't I? So that's going to be minus pi over 3. So my 2 values that I'm going to need are plus and minus pi over 3. I then need r so that I can give the coordinates, the polar coordinates, which is what I've been asked for in the question. So I'm just going to sub one of these values back into the easiest curve, which is this one. So r equals 3 cos 3, r is 2. Now, because I know the curves are symmetrical, because of my knowledge of polar curves, I'm just going to be able to use 3 over 2 for both coordinates. So the points of intersection are 3 over 2 and the angle over 3 and 3 over 2 again, and this time minus. So that's part B. The reason they've asked me to do this is because I need to know angles where the dotted lines are. I'm going to work with the top part of the curve have a think about setting up my integrations. We should call this area here A1, and that's the area between the initial line and this line here. I now know the angle here is pi 3. And we'll call above the line area 2. So to begin with, I'm going to work out the area of area 1. A1 is going to be integral, so forget the half in front, between the initial line, where the angle is 0, and point of intersection, 3. And the curve that is creating that area is the cardioid. So that's 1 plus cos theta. And we're going to square it because it's r squared in 4. So expanding equation, get 1 plus 2 cos theta plus cos squared. Now I need to integrate. Oh, look, I've got a cos squared. I need my double angle again. Careful, watch your halves and be accurate. So we've got 0, 2, 3, 1 plus 2 theta. And we have half cos theta and a half. I'm now ready to integrate. So that becomes a half theta plus 2 sine theta plus sine of 2 theta plus a half theta. Evaluate that between Norton. I could have combined the theta and the half theta at an earlier stage before integrating. You'll work out the best way of approaching the simplification as you practice. So I sub in and simplify. And in this case, we will get an ounce of quarter pi plus 9 over 16 root 3. So that's area 1 in exact form. I'm now going to evaluate area 2. So I'm looking at this area from the line pi over 3 up to the circle. Area 2. Have a think about what limits I'm going to need. My bottom limit is going to be pi over 3. What's my top limit going to be? If I'm not sure, I need to use my technique where I let r equals 0. So let's have a think about that. What are the limits? R equals 0. Working with the circle. So we have equals 3 cos theta. Solving that, theta going to be pi over 2. And I could carry on, but I know that the curve is going to come to here and reach 0. Theta is pi over 2. I could establish the other one, but again, we're dealing with symmetry. So A2 is going to be a half integral between pi over 3 and pi over 2. And we're going to be plugging in 3 cos theta, squaring it, and separating. So we have squaring this, we're going to get 9 over 2. Cos squared theta. So again, it's a double angle substitution. Plus 1. We can put, actually that's going to have a half, isn't it, with it, so let's make that a 4 theta. Integrating, we will get a half cos 2 theta 2. Evaluating, I will achieve a result which is 3 pi over 8 minus 9 root 3 over 16. So I now have area 1 and area 2. So my total area is going to be these two added together and then multiplied by 2, so that I find this area here and then I double it to find this area here as well. So that's 2 times A1 plus A2, which is times I plus 8 3, giving me a final answer of 5 pi over 4. So 2 times 2 areas added together. We're working with there, and my final answer is 5 over 4. Now, I've done the calculation this way, so you can see the individual areas being found and how the limits have worked. I could simplify my working a little bit further, provided I've understood that I'm which areas I'm working with and which parts I'm doubling. Let's just have another little look at the graph that we've got here. Now, I have to find this area, which we know is the same as this area down here. And I have to find this area, which we know is the same as this area here. So, in order to simplify the number of halves and everything that I have everywhere, I could have done my working slightly differently. I could have found 2 times area 1, and that would have allowed the formula to be simplified. So if we have a little think about that, we'll just put this at the top. So thinking for simplifying work. I could have used 2 times area 1 and 2 times area 2 to simplify. So 2 times area 1 is 2 times area 1 plus 2 times area 2 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 used 2 times the half the integral r squared d theta to generate 2 times a1 or 2 times a2. Why would I do that? Because this will obviously cancel, and it just shortens the working slightly. I'm only mentioning it as at the end of the question, because it is really, really important that you do not get the formula wrong by forgetting the half at the front. And you must only ever do this if you thought through the whole question and you are using it to deliberately simplify your working. One other thing that I want you to think about very carefully is limits. You must have them in the correct order. Here we used a1 from 0 to pi over 3, and that found the area a1. Now, usually when you swap round the limits on an integration, you just change the sign. However, that is not the case in polar. If I were to work with the limits pi over 3 at the bottom and 0 at the top, I would be going from pi over 3 round the pole and arriving at 0. And that will produce me a very different area. So, to summarise, when doing polar coordinates, think really carefully about the areas you're finding and divide up the shape appropriately. Think about the symmetry of the graph. This thinking up here only works if we have a graph that is symmetrical about the initial line. So think carefully about your area, think carefully about symmetry, and then think really carefully about the limits and the order that they are in. And then and only then, when you've thought it through, apply the formula and do the integration.